Hello, everyone. Welcome to the course of Fundamentals of Additive Manufacturing Technologies. Can I get a heads up if my slides are visible and am I audible?
Yes, sir. Slides are visible and you are audible, sir.
Yes,
Okay, perfect. Thank you so much. So this is the week two tutorial session of this course. Let me remind you once again, there are three tutors who take this course. So one is on Friday, one is on Monday, that's today, and one is tomorrow, that's Tuesday. So you can attend any of these three sessions. You are not mandated to attend all of these three sessions because the course content will be same for all of these three sessions. And but to be frank, the teaching style will be different. As I told you in the previous session, the teaching style will be different for all of us. But the course content will probably remain the same. So it's not mandatory to attend all of these three sessions. And yeah, it's up to you whom you're comfortable with and which you like better. There is no such thing as to attend all of these three courses. So yeah, in this 12 weeks course, we'll be studying about fundamentals of additive manufacturing. What are the different types of additive manufacturing technologies? And some basics about additive manufacturing, why additive manufacturing is necessary. And yes, so in week one, we got introduced to additive manufacturing, what is additive manufacturing and various types of additive manufacturing. In this in this week two, we'll be diving deeper into that. Uh, the course coordinator for this course is Professor Sajjan, and I am your teaching assistant. Just to give you a brief recap about what we studied in the previous session, we got introduced to additive manufacturing. What is additive manufacturing? Additive manufacturing is a set of fabrication method where we are fabricating the material by layer addition, which is different from the subtractive manufacturing because there are a lot of post-processing techniques utilized in case of subtractive manufacturing, which is completely avoided in case of additive manufacturing. The advantages are like we can print complex geometries. This is quite faster printing, and we have huge degrees of freedom. And it is the applications lies in various sectors as well. Then we got introduced to the different types of additive manufacturing technologies, like the 7 groups according to the ASTM standard. One is binder jetting, material extrusion, powder bed fusion, VAT polymerization, directed energy deposition, material jetting, and sheet laminations. We also went into details about all these seven types of processes. If you want a recap of these all these processes, you can just go back to YouTube and search for the lecture. That will be helpful. Then, yes, we solved some initial questions regarding this additive manufacturing introduction. I left these two questions to be solved in this session because some of you are not confident about the numerical questions. So I'll give you 5 minutes. If you can give these two questions a try, then after I will be solving these questions. I'll give you 5 minutes. May it be wrong, you should give it a try. It doesn't mean that you have to do it the correct answer. It may be wrong. Just give it a try. Anybody has any idea of how to proceed with the answers? And just type it in the chat box. How to proceed? Hi, Sirtaj. You are right about that. But can you like dive deeper, like how to do it? You're right, but
Sir, we have 3 points. Then first of all, we
Mhm.
find two vectors. Means we have 3 points. Then we find out AB vector and AC vector. Then by the cross product, we can find a perpendicular vector to the plane. And then if we have a perpendicular vector and it points on the plane, then we can find a vector r dot vector n cap is equal to 0. It is the equation of the plane. Then we can find the equation of the plane by this method.
it was Sirtaj, right? Who
Yes,
was
sir.
it? Who answered? Yeah,
Yes, sir.
perfect, perfect. Thank you so much, man. It was great. The answer is perfectly right. But there is one easy method to approach to this. What you said is also correct. I would agree to that. But the question has asked that find the equation of the plane. So we do not need to calculate the unit vector to the plane and to the normal to the plane. We do not need that much of calculations. We can directly find the equation of the plane in terms of x, y, and z. How to do that? Let me just tell you how to do that. Okay. So what is the equation of the plane according to the? Do you remember what's the equation of the plane according to professor? It's x minus x1, y minus y1, z minus z1, then x2 minus x1, y2 minus y1, and z2 minus z1, and z3 minus z1, z2. Sorry, x3 minus x2, y2, y3 minus y2, and z3 minus z2. This will give you the equation of the plane. Here, x, y, and z, we will find the equation of the plane in terms of x, y, and z. Fine. x1, y1, z1, and x2, y2, z2. Similarly, x3, y3, z3 are known because this is x1, this is y1, this is z1, x2, y2, z2, x3, y3, z3. Everything else is known. X, Y, Z, Z is unknown. We'll be finding the determinant. Sorry, we'll be finding. Sorry, this is a matrix, not a determinant. This is a matrix. This will give you the equation of the plane, right? But the thing is, before using this matrix, we need to check one thing. What is that? Can anyone say what is that before using this equation? Okay, let me tell you. Before using this equation, it 3 points can form a plane. How can we know that? That means either two of these, at least two of these points are not collinear. Then only these 3 points can form a plane. For example, if these 3 points are collinear, there is no chance of forming a plane. It will be a straight line. But one of these points are non-collinear to each other, then there will be a formation of a plane. A triangle is formed. So we have to check this first. To check the collinearity, we have to find the determinant of this 2, 2, 0, 2, 4, 2, 4, 4, 2. We have to find the determinant. If it is not equal to 0, that means these 3 points are not collinear and a plane will be formed. And after confirmation of this, we'll be using this matrix to find the equation of the plane. This is how we solve it. Got it? Got an idea? Yes, sir. Can you mute yourself? The person who is
తప్పదు నాతోటి మాట్లాడలేదు నా తప్ప ఎవరు తప్పు
excuse me, can you mute yourself?
సమానం కాదు ప్రేమ సమానం అని చెప్తున్నాను నేను ఇన్స్టాలో
Okay. Sorry about that. Okay. So is everyone clear about this? How to proceed with this question? Yes or no?
Yes, sir. Clear.
Okay, perfect.
Yes, sir.
Okay, thank you so much. Then let's go to the next question. Just a second. Okay. So the question says, how many triangles will be required for deviation tolerance? Deviation tolerance is given. This question is regarding the deviation tolerance. You may remember to represent a circle of 10 mm radius by STL format. This is a question from the deviations. If someone can give me an idea of how to solve it. And here, what is given? D is given, deviation tolerance. This is not angle tolerance. This is deviation tolerance. So what's the formula for that? Deviation tolerance. I think these are the questions which are there in the assignment as well. So if you solve these questions, it will be helpful for your assignments. Anybody remembers the formula for deviation tolerance? Anyone wants to try, or shall I just solve it for you? Okay, let me solve it for you. So the formula for deviation tolerance is given by R minus R cos
Sir,
theta.
100.
Sorry. Who was that?
Sir, Mohammed Sirtaj, 100.
Oh, hi, Suresh. Yeah, you're correct. Perfect answer. Yeah, it's 100. Perfect answer. Can you just guide me through how you solved it?
Sir,
Siraj? Yeah,
tolerance is hello.
yeah.
Sir, tolerance is given 0.005 and radius is 10 mm. Then, sir,
Mm-hmm.
we can apply the formula. Uh,
Mm-hmm.
Sir, 1 minute. H is equal to R 1 minus cos pi by n. Then, sir, after
Okay.
putting the values, maybe, sir,
Okay.
it is
Perfect.
approximated 100.
Yes. Perfect. Great answer. Great answer. Thank you. So the formula is R minus R cos 180. That is, as he said, that's pi 180 upon n equals your deviation tolerance. This is the formula. Where the formula arised, or how did we derive this? You can go to the professor's lecture. You can get a better idea of how he explains it, because he explains it with the figure. I don't want to waste your time doing that. You can go to the professor's lecture and then get to this formula. So how will be applying this? This is the formula. How will we applying this? We know the deviation tolerance. Sorry, we know the deviation tolerance. It's given us 0.005. So 0.005 equals, if we take R common, R is also given here 10 mm. R common 1 minus cos 180 upon n. Here n represents the number of triangles. How will you find the value of n? N will be equals to 180 upon cos inverse 1 minus 0.005 upon 10. This is the formula you'll be using. Just I have not done anything. I have to just find out the value of n. How will you find out this? Will be just divide both the sides by 10. This is just pure mathematics. Dividing both the sides by 10, then subtracting 1 from both the sides, then multiplying both the sides by minus 1. We'll be getting arriving at this formula. So this will give you a answer of 100. N equals 100. So how many triangles will be required? 100 triangles will be required for deviation tolerance of 0.005 and for 10 mm of radius by STL. This is how you solve the question. So I think most of the questions in your assignment is also similar to this. So this will help you to solve the questions. We'll be discussing the assignment solutions next week, because this week the assignment solutions have not been released. So most probably we'll discussing the answers in next week. And if you still have any doubts, we can discuss under that. Okay, let's go to manipulation of STL files, which was the course of this week's, which was the content of this week, sorry. So we studied there are two manipulations of STL files. One is rotation of the figure and one is translation of the figure. What is rotation of the figure? We have created a figure. Now we want to rotate the figure along variety of axes, three axes, X, Y, and Z axis. So if we rotate the figure by an angle theta along X axis, this is the formula we'll be using, rotation matrix. If we rotate it along y-axis, this is the formula we'll be using, rotation matrix along y-axis. And if we rotate along z-axis, we'll be using this matrix. And angle is theta. Theta is the angle of rotation. Theta x, angle of rotation along x-axis. Theta y, angle of rotation along y-axis. And theta z, angle of rotation along z-axis. This is the formula. The coordinates of the rotated point can be given. This is the overall formula, because this was separated into three. This is the overall formula we'll be using if you have multiple triangles in the figure. Then The second mode of one is rotation, and the second mode, which I said, is translation. So if we are translating one point or translating multiple points in an STL file, the formula to be used is this, where X, Y, and Z is the translation we will be using, the translated points or the values to which it is translated. Just addition. So the manipulation of the STL file is done in two ways. One is rotation, one is translation. By While we are rotating, we'll be using the formula as I mentioned in the previous slide. While performing the translation operation, we'll be using this formula. So now we'll be solving some questions only based on translation, only based on rotation, and including both. Like we are translating as well as rotating. This will help you further in help you with answering the questions as well. Let's solve this question. This is the question. Just give it a try. I will give you 5 minutes. There are two questions. I'll give you 5 minutes each. Just solve this question. If you are still struggling with that, I can help you out. This is a question on translation. You can see the triangles are translated. Somebody is asking some question. Just to give me 1 second. Yeah, sorry. So the triangles are translated one unit along x-axis, one unit along y-axis, and then one unit along x-axis. So the trick is we are moving 2 units along x-axis and 1 unit along y-axis. So what will be the unit vector? This is quite easy. You have to just add there. Anyone got any idea how to proceed with that, or shall I just help you out? Okay, I'll just help you out with the solution. So there are three vertices. It's a triangle. So there are three vertices of the triangle A, B, and C. Those values are given to you. 110, 110, and second vertex is 121, 121, and the third vertex is minus 2, 2, and 1, minus 1. Sorry. These are the three vertex which is given. So how will you solve this? We are translating 1 unit along x, 1 unit along x. So plus 2 units along x-axis, then 1 unit along y-axis, plus 1 unit along y-axis, right? So what is the translation matrix? What will be the translation matrix? Translation matrix will be x-axis 2, 2, then y-axis 1, and z-axis. We are not moving along z-axis. So your translation matrix will be 2, 1, 0. Right? Everyone with me? Yes or no?
Yes, sir.
Perfect.
Yes,
Yes.
yes, sir.
Good. So let's see about point A. Forget about point B and C. Let's see point A. Point A, the point A, the matrix is 1, 1, 0, right? And then we are translating it. And as I said, just for translation, we'll be just adding it. Adding the translation matrix. That is 2, 1, 0. We're just adding them. So what will be the new point? New point A, that is A dash. What will be the new point after translation? It will be 3, 1 plus 1 is 2, 0. This is the new point A dash. Similarly for B, which the new point will be B dash. What will be the thing? 1, 2, 1, and then the addition of the translation matrix. That's 2, 1, 0. It will be 3, 3, 1. This is point B. What about point C? Point C will be minus 2, C dash, the new point, 2, minus 1, plus the translation matrix. That's 2, 1, 0. It will be minus 2 plus 2 is 0. 2 plus 1 is 3. Minus 1 plus 0 is minus 1. Now you get it. New points A dash, B dash, and C dash are these points 3, 2, 0, 3, 3, 1, and 0, 3, minus 1. These are the 3 points, 3 coordinates, right? Then how will you find out the unit normal? What will be it has asked the unit normal, right? You have point A, point B, point C, which are translated to point A dash, B dash, and C dash. You have to find the unit normal of this A dash, B dash, and C dash figure. How will you do that? Very easy. Siraj, maybe you can explain because you answered the first question in the same format we'll be doing this.
Sir, we have points A dash and A, then find out the vector A dash A and divided by the modulus of the vector and same as B dash and same as.
Perfect. Perfect. We'll be finding the vectors A dash B, A dash C dash, and then we'll be finding the unit vector by dot product divided by the more magnitude. A dash B dash dot A dash C dash divided by the magnitude. This will give you the unit vector corresponding to the facet normal. That's how you solve this question. Did you get it?
Yes, sir, yes.
Perfect. Okay. Okay. Then this is the interesting question. This is the same question, but there is one more thing in here. There is a rotation along z-axis. Try to solve this question. So there is a translation as well as a rotation. Combination of both. Can anyone tell me the translation matrix? What will be the translation matrix? Just the translation matrix.
Zero, one, one.
Perfect. Great. One thing solved. Then it's rotated by 90° along z-axis. Can anyone tell me the rotation matrix? Remember the formula. Let me go back to the formula again. This is the rotation matrix. And it is rotated along z-axis, right? What will be the value there? 90° rotation. This is the rotation matrix. Can anyone tell me? What is cos 90?
Sir, 0, 1, 0, minus 1, 0, 0, and 0, 0, 1.
0, -1, 0, 0. This one will be sine 90 is 1, 0, 0,
1, 1,
and
0, 0,
0,
and 0,
0,
0, 1.
1. Perfect, perfect, great, good. So we have our rotation matrix, we have our translation matrix, right? Then let's come to the question. What does it say? First, the triangle is translated, right? Triangle is translated, and we have points A, B, and C. After adding the translation matrix, as we did in the previous question, what will be the answer? Point A dash will be 1, 2,
1, 2, 1.
1. Perfect. Point B dash will be 1.
And B dash is 1, 3, 2.
Perfect. And C dash will be
And
-2.
-2, 3, 0.
Perfect.
B,
Perfect.
0.
Perfect. This is A dash, B dash, and C dash after translation. Then after translation, we are doing a rotation, right? How will you calculate the rotation? If it is translation, we just add it to the matrix, right? But rotation, how will you do that? This formula. See, the rotation is multiplied with the matrix. You see, this is the translation which is added to the matrix. But while rotation, here is the multiplication. Rotation is multiplied with the matrix. So what do you have to do? This is your new matrix. 1, 2, 1. This is your new matrix. You have to multiply your rotation matrix with each of these individual points. You have to multiply this with all of these individual points. 0, -1, 0, 1, 0, 0, 0, 0, 1. You have to multiply these two matrices to give you each points A double dash, B double dash, and C double dash after rotation. Did you understand what I'm trying to say? Yes or no?
Yes, sir.
Yes, sir.
Perfect.
We need to
So
multiply all the points with this matrix.
yes, yes, all the points individually with the rotation matrix. So in these type of questions, you need to remember the formula for rotation, what you are using. Translation is simple, no need of remembering anything. But for rotation, you need to remember the formula. And you have to see the sequence, how it is done. In this question, first we have translated, then we have rotated. There will be some questions where the rotation will be first, then we will be translating it. Translation is purely easy. We do not have to do anything, just add to that values. But rotation, we need to multiply the matrix. It's easy as well, but just be careful while multiplying the two matrices. These are the things we'll be taking care of while solving these type of questions. Everyone is with me? Everyone clear?
Yes, sir.
Okay, perfect. Thank you so much. Okay, now we solved a lot of questions. Let's go to some theoretical questions. Not theoretical discussions, not probably questions, theoretical discussions. Then finally, we'll be solving some more questions as well. Okay. So in this lecture, we also got introduced to support structures. What is a support structure? The thing is, while 3D printing a material, the material will always not be parallel to the build plate, right? If the material is parallel to the build plate, it will be easy to print because we do not need anything. It's just parallel. We just print it on the build plate. But sometimes the structures can be complex. That is, maybe it is at an angle. Maybe it has an overhang structure. Like for example, you see in this T. When you create this T, what do you have here? This is an overhang structure. Somebody may tell that we will be printing the T in a other way direction, like we'll be printing in this way, so that we will be totally avoid the support structure. Perfect. That's correct as well. This is one of the structures. T is one of the structures. We can print it vertically so that to avoid using support structure. But what about H? What will you do with that? Can you avoid using support structure in that? No, right? We have to use support structures for this overhang structure. Then you'd say that, okay, why can't we print directly? Why will we need support structures? The reason we need support structure is that prevent shagging and collapse. The thing is, if there is no material at the bottom of this, the printer will start printing these two layers first. And then when it comes here, there will be loose powders here. It will just print it here. Of course, it will just print here, but there will be just loose powders within that, below that. So the solidification will be not proper. And the strength of this part will be weak. It will be very weak. That means it will collapse easily. That's the reason we need support structure. Then maintain geometrical accuracy. If somehow you say that you got this material printed somehow without support structures, your accuracy, your geometrical accuracy of this material, of this structure, sorry, of this structure, along with that, the surface finish will be very bad because there are loose powders with below this point. And another most important point is dissipate heat and reduce distortion. So as you know, we are using laser or any other laser or light to print these materials. We are using high power energy, high energy electrons, high energy laser to print these materials. So there will be a lot of distortions developing in the material, and the heat extracted should be transferred to the build plate. For these structures, the heat extracted will be easily transported because there is a contact with the build plate. There is a huge contact. But while printing this structure, there is no contact with the build plate. How will the heat transfer takes place? There are loose powders. Loose powders are very bad conductors of heat because they are not closely packed. So how will the heat dissipation take place? Only by the use of support structures. So therefore, the support structures are quite necessary in case of overhang structure, overhang models or overhang structures if it is present in a material. Let's see some YouTube videos which will give you like pictorial idea about why support structures are necessary. I think these are like 10 or 15-minute long videos, so please bear with me. Just a second.
Hey guys, today we're going over tuning basics and how to tune your print to get the perfect part every single time. The next setting we're going to go over is supports and support settings. Now this is really critical if you have complex geometries where there's a part comes up and goes over here, but there's nothing underneath it attaching it to this part. So the key to supports is that the printer can't generally print in mid-air. So you have to give it a surface to print on top of. So this is what we call supports, where basically it's sacrificial material that just builds up until the point where the part begins, that flat spot or bridging or something of that nature, and it supports that material. Now, the most important part of supports is your interface layers. Depending on your layer height, this is going to change. At point 1, you might want to leave 2 separation layers. At point 2, usually 1 separation layer is good enough. And again, this changes based on the material. If we're printing PEEK versus printing PLA, we need different settings for the PEEK because it's going to fuse together. It's 400 Celsius, you know, and the PLA generally is easy to remove and you're only down at the normal 200 Celsius temperatures. So the settings are going to change per material. So a separation layer is basically, it's going to build up the supports and then it's going to stop. And then your part is going to print another layer and then it's not going to print over here. But then on the next layer, it's going to start printing on top of the support. So that's one layer where there's no material and it allows the supports to cool enough to where the next layer on top doesn't bond to it as well, but it still should lay flat. So there's a lot of settings involved with that and getting that dialed in based on each material. But usually the automatic setting in your slicer is going to work just fine, especially for basic materials like PLA, ABS. Now, sometimes your slicer is going to place supports where they can't be easily removed. Like if you're printing something that's hollow and you have supports everywhere, it's going to try to put supports inside that hollow object. And unless you have a big cavity or if it unscrews or something like that, you're not going to be able to get those supports out. What you want to do, there's a setting in most slicers that lets you build supports from the build plate or everywhere. So from the build plate only is basically going to keep everything on the outside. It's not going to print anything where you can't get it out. If you want to get a little more advanced with this, you can actually download Simplify 3D, and that allows you to place supports wherever you want. Fully customize it, works really great. We like using that when we need custom supports. So the best way is always to design your part or find a part that doesn't require supports, because support can be hard to remove, it's a waste of material, it adds time to the print, it's just, if you can avoid it, awesome. And there's a lot of different ways to avoid it. The best way is always going to be avoiding supports entirely. And there's a lot of advanced techniques that we use to do that and to help our clients create a part that's going to print well and still work in the geometry that they need. But for beginners, and if you're printing in PLA, you should be fine just with the automatic settings. Now, this is really something to take into account, because if you're printing a large part and you have it oriented on the bed in a way that's going to make it use a lot of support material, it's going to just basically, you might end up printing more support than your actual part. And there could be an easy way to reorient that part, just as is with no modification, to use less supports. So avoiding supports or using as little supports as possible is generally the best way to go. When you get really good at it and you've tuned it in and you're really familiar with your material, then you can actually sometimes get away with things that you couldn't before. You can tune in special cooling or special temperatures to allow it to print these other features without supports. There's also advanced printers on the market that use dual extrusion. So they have two different nozzles extruding two different materials. And this one will be the normal material, and then this one will be your soluble support, whether it's water-soluble PVA or if it's something like HIPS, where you dissolve it in solutions and chemicals. But it's printing two different materials at the same time. So this actually allows you to print impossible objects. You could print a sphere within a sphere within a sphere, and just throw that into the solution, let it sit for however long until it all dissolves away, and then you've got your impossible object. For the high temperature materials like PEEK and PEI, there's no really good soluble support on the market yet, so generally we just use PEEK supports for PEEK parts. If you're a beginner and you're thinking about getting the soluble supports, I don't recommend it to start, just because it is much more difficult to tune in two nozzles as opposed to just one. So in the beginning, just start with one, learn the basic process, and then when you're more advanced, move on to the different kinds of supports. Whether you've got a $300 printer or a $30,000 printer, always.
Okay, so now we got an idea about why superstructure is necessary and like why is it required. But the thing is, the video said that most of the times we try to avoid printing support structures. The reason is that removing support structures adds on an additional task of post-processing. We have to remove the support structures, which is an additional task. We need our material to be ready immediately after printing. So by any chance we get, we try to avoid printing support structures. But if it is absolutely unavoidable, then we need to print it. That's what it was trying to say. Let's watch another video, which will give you a very elaborative idea about the support structures. This is, I think, a 15 minutes video. Just bear with me.
This is your guide to 3D printing support material. We'll cover how to use it efficiently, as well as how to tweak your slicer to get it to peel off perfectly.
As I told you, we have to peel off the support structures after printing. This adds up an additional task if you're using support structures. Then in this video, it will try to peel off. It will try to show you everything about that.
Personally, I don't really like using support material. In fact, I design my parts to try and avoid it. But sometimes it just can't be avoided. And in those cases, I want it to be as easy to use as possible. My patrons requested a video on this topic, so here we are, covering multiple scenarios as well as multiple slices. Let's start from the beginning by asking what is support material and why and when do we need it? Here is a simple test piece to show what a 3D printer can and can't achieve when building up layer by layer. On the left, we have an overhang, in this example 45 degrees. In the middle, we have a bridge supported on both sides, and then on the right, we have an unsupported section cantilevered. Let's preview this print and see that in the earlier stages, our angled overhang is in effect. We can see on the left that the 45-degree overhang prints really without any trouble at all. And as the print progresses a little further, we can see that we're going to have our bridge in the middle, as well as our cantilevered unsupported section on the right. If you're new to 3D printing, you might be amazed just how good they are at bridging. Despite being a molten material, the part cooling fan will solidify the plastic in mid-air. However, on the right, the overhang supported on only one side is drooping badly, because there's not enough support there to hold up the extruded plastic. Amazingly, it does recover quite well by the end of the print, but in other cases, such as this key ring, we won't be so fortunate. Previewing layer by layer, we can see that the legs will be fine, but as soon as these arms are introduced, the tip of them will be printing in mid-air, so to stop this from being unsupported, we introduce support material, shown here in grey. You can think of support material like scaffolding on a building, a temporary structure designed to hold pieces from falling to the ground until the rest of the structure is completed. And once the structure is complete, just like building scaffolding, we can remove it as it's no longer needed. This means that 3D printing support material is sacrificial and therefore will use up extra time and filament. So coming back to our original questions, support material is additional sacrificial plastic that we add to the print to support sections that would otherwise droop down and possibly cause the print to fail. Before we continue, we need a suitable test model to demonstrate the principles, and I think this support test by FOTMAS is ideal. If we examine this model, we can see that the geometry will cover a variety of scenarios where we might need support. Firstly, we have a 45-degree overhang, then we've got a filleted overhang, which starts close to vertical and gets steeper as it goes. We've got an overhang with a flat surface, we have an overhang with the circular bore on the inside, and we have one more overhang on top, cantilevered, but most importantly, this sits above the model rather than sitting on top of the bed. The first thing I'm going to do is to slice it and print it without any support material in place, just to see how it goes. Like this, we use minimal filament, and this took just under 15 minutes. And considering no support, honestly, it doesn't look too bad, but there are droopy sections where the plastic is messy because it's been extruded in mid-air. So let's see how much we can improve this print by turning on support material.
Did you see this? If you're not using the support material, there is a lot of extruded part or the part geometry which is damaged if you're not using support structure. This was the distortion. This is due to the distortion, which I mentioned earlier.
But there are droopy sections where the plastic is messy because it's been extruded in mid-air. So let's see how much we can improve this print by turning on support material. Next, we'll answer the question, what are the available types of support material? And at the time of recording, there's two to choose from, traditional and tree or organic. Traditional is by far the most common, so we'll start with that. It's also the most like the scaffolding example we looked at from real life. Let's come back to our slicer and turn support material on, slicing with the defaults at this stage. All of the support material is shown here in green, and let's break down exactly what we're seeing. Most support material has some sort of thicker element on the bottom, which we can refer to as a raft. This is to give a stable foundation for what's going to be built on top. We'll then have a much sparser pattern, built up in layers vertically, and this will form the bulk of the support material. Perhaps the most important layer is what we call the interface layer, shown here in dark green. This is designed to provide a solid platform on which the actual model is then printed. However, it's not printed on top directly, there's always a subtle air gap in between to ensure they don't fuse together permanently. We'll also note that by default, this upper section has not been supported, but we'll get to the settings for this shortly. What you've seen so far is in my slicer of choice Super Slicer, but you'll find that most slicers build up their support material with these same elements, they just might call them by a different name. Across various slicers, the approach is still more or less the same, so now let's look at how to tweak these parameters to get that oh so satisfying to remove perfect support material. This is where variation in slices makes things tricky, but I'll try my best to cover most of the popular ones. So we have Cura as a standalone as well as Simplify 3D, and the other popular slicers started from Slick 3R, which was forked by Prusa Slicer, which was forked to make Super Slicer, and also forked by Bamboo Labs to make Bamboo Studio, and then that was forked by Soft Fever to make Orca Slicer. When you hear me talk about Prusa Slicer derivatives, we're talking about Prusa Slicer and everything that followed, as the names of the settings seem to be quite consistent. We'll start with some general settings that affect how the support is applied. Remember this section up the top, which is unsupported because it's above the rest of the model. To get support there, we need to change from build plate only to everywhere. And now when we reslice, we can see that this area is supported. Unless your model explicitly has a section like this that does need support above the model, I would recommend leaving the setting on build plate only, as less support will be generated in general. The next common setting is called overhang threshold, or in Cura, support overhang angle. If we look at the curve on our test model, we can see it's nearly vertical down this end and almost horizontal up the top. If we exaggerate this setting, setting it to 10 degrees, we can see that support material is not applied until the model is almost horizontal. And if we exaggerate it the other way to 80 degrees, we can see that support material is applied much earlier in this curve. The right value will depend on your model, but to work out a good default, you can download and print this torture test from the description and find out at what angle of overhang your printer starts to struggle. With the general settings out of the way, let's start to look at specifics, starting with our bottom or raft section of the support. The amount of control we get over this depends on the slicer. For instance, for Prusa Slicer and derivatives, by increasing the raft layers and then slicing the model, we can see that it adds a raft underneath the entire thing, not just the support material, and you probably won't want this. So instead, the setting we want is first layer density. Here's the default 90%, and here's a much lower 45. You're probably going to want to keep this quite dense just to give it additional grip to the bed. In Cura, the equivalent setting is Enable Support Brim. We can see without it, we don't have much grip on the bed, but turning it on and reslicing will give us a much denser section for maximum adhesion. Simplify 3D handles this explicitly with base support layers, with the default being 2. Generally, the aim of our support base is to get a good solid platform to build on, so we want it to be fairly dense without wasting too much filament. Let's move to our core support material in the middle. This simply acts as a scaffold, but we can still customize it quite a bit. The density of this section is handled differently in various slices. It's called support density in Cura and support infill percentage in Simplify 3D. This is like your regular infill density. Here's the default value of 20%, and here's the value up to 50%. An equivalent of this for the software derived from Prusa Slicer is a spacing setting. Here's the default 2.5mm, spacing of 1mm, and here's 0.5mm, everything packed a lot tighter. Some particularly intricate prints might need this density increased, but for most prints you can leave the percentage low simply to save filament. We can optionally wrap walls or a sheath around the outside of our support. Here is this setting off, and here it is on with a continuous exterior wall. In Cura, this is called support wall line count, and in Simplify 3D, support outlines. This is personal preference, but I like to have this on as it holds the support material together in chunks and makes it easier to grab and rip off with pliers. What about the XY gap between the support material and our actual model? In Prusa Slicer and derivatives, this is called XY separation and can be expressed as a percentage or in millimeters. In Cura, it's called support XY distance, and in Simplify 3D, support horizontal offset from part. Here's a typical close gap that you'll see by default, but I actually like my gap to be exaggerated and large, as it gives more room to fit tools in between the support and the model to help lever it off. Now our most important section, the interface. If you wanted to, you can change the thickness for this, including setting it off. In Cura, it should be ticked by default, and we set the thickness in millimeters instead of layers. In Simplify 3D, it's off by default, and we change the upper dense support layers to add it. Most of the time you're going to want this pretty dense, as that will give the flattest surface to build on top of. However, if you'd like to save filament, or perhaps you'd like to make this easier to peel off, in Cura you can lower the density, with this grid being quite sparse, or here in 80% being a lot denser. Simplify 3D also has a percentage for changing the interface density. In Prusa Slicer derivatives, it's a little counterintuitive. If the interface spacing is set to 0, it will be dense, but we can manually override that with a millimeter value, which will add gaps in between the extrusion, making it less dense. It's important to note that when we see bottom interface layers, this doesn't affect the support raft touching the bed, but rather the geometry where a model will require support that's built off the model instead of the bed, so the lower interface is the section just above this. Finally, our most important parameter to tune, which is the air Z gap in between the interface and the model. Prusa Slicer derivatives call this the Z offset, and we have a value for top and bottom. Cura calls this the support Z distance. And Simplify 3D calls this the upper and lower support separation layers, unique to this slicer because it's not measured in millimeters. When we see a bottom Z distance, this is talking about the gap where support is built on top of the model and relates to the air gap in between the model and the lower interface. These vertical air gaps are a setting you should do some trial and error test prints with. Here we can see a series of test prints where I experimented with the air gap to try and find the best setting. For the sloped parts of the model, the removal of the support material is actually quite similar. The larger of the two gaps can be removed completely by hand, but as we head to the tighter two, we need a tool to get them going, and then the final peel happens with our fingers. When it comes to the 90-degree section, however, the difference is more apparent. With the largest gap, there's room to slide the tool down and get the peel separation started. But from the second largest gap, we need to use a flat scalpel to get in between the two halves and pry the support material off. However, we can see that the separation is not entirely clean. The second tightest once again requires a blade to get in between the two, and it feels like I'm cutting a little bit instead of just separating the support material. After this initial phase, I can get my pry tool in to get it off, but once again, the separation is not very clean. The smallest gap is quite difficult because it's hard to even get the tip of the blade in to start separating the support section. Eventually, after a lot of cutting and wiggling and then using the pry tool, I get the support material off, but there's quite a lot of it left on the underside of the model. And this is the compromise where we're trying to find the sweet spot. Too small a gap and we'll have nice flat layers, but the support material will be difficult to get off cleanly. Too big a gap, the support material will peel off easily, but the layers will droop and not exactly be flat. Each printer is different, and it's all about finding that Goldilocks zone in the middle. There are many more settings than this between the different slices, but what we've covered so far I think are the most important ones. So far we've looked at traditional support material, but what about tree or organic? If traditional supports are like scaffolding on a building site, then organic or tree supports are like thick vines growing around a structure. Here's a comparison with traditional supports versus tree supports, and you can see their approach is entirely different even though they still complete the same task. In Cura, we select this by changing support structure from normal to tree. In Bamboo Studio and Orca Slicer, we change the type from normal to tree, and Prusa Slicer will now let you change the style from grid to organic, but at the time of recording you have to scroll past the stable release and download one of the 2.6 alphas for this feature to be included. Organic supports aren't currently offered in Simplify 3D, and Super Slicer doesn't have them either, but hopefully this will be included later on. Tree supports might look different, but they still have the same structure as traditional, with a raft on the bottom, a midsection that flows more organically, and of course an interface layer on top to touch the underside of the model. When you switch to them in Cura, you get some specific settings for angles and minimum and maximum thicknesses, and in Prusa Slicer we have this section at the bottom with exactly the same type of thing. The real question is when to use them, and I would argue that our existing test model is not ideal. So how about something more organic in the form of this Earth Dragon by Alex? This dragon has some large overhangs and clearly needs support underneath. But looking at traditional supports, this becomes quite awkward as they struggle to match these contours. So let's change them over to tree, accept the recommended settings, and slice again. Already we can see that this looks completely different. So there's nothing left to do but to print a test to see how easy it is to remove. Fun fact, this might be the first print I've ever completed with tree supports, but I used the settings that I already tuned in for this printer, most importantly the Z air gap between the interface and the model. In my opinion, this process turned out really well, and most of the support material could be removed just by pulling it in the right direction with my fingers. We can see that the organic supports contour nicely to this rounded belly. The hardest support to remove came from this section, but I didn't need my blade, instead just my prying tool to apply a little bit of pressure to each side of the support, and then it just pops straight off. The end result is a very clean underside to the model. Therefore, I'm calling this one a success. Tree or organic supports are a really nice option depending on the model that you're printing. Let's finish with using support efficiently. Support material takes up extra time and filament, so how can we be intelligent about applying it? Simplify 3D has a pop-out control panel for support material, and then we can generate these automatically. What's really nice now is that we can click to remove individual support sections, and we can also click to add them in specifically troublesome areas, giving us more control over where support material is placed. In Cura, if we click on the model, we can then come down to the support blocker icon and then click around the model to prevent support from being added in those locations. It can be a little bit tricky to get to all of the areas that you want, so it's good to know that you can click to select these models and manipulate them like any other 3D model you've imported, scaling them and rotating them to suit and moving them into the ideal position for what you're trying to achieve. Now when we slice, we can see that for the most part, support material has been omitted from any of these areas that these boxes overlapped. Prusa Slicer and derivatives perhaps have the most control. By clicking on the object and then coming to the Paint on Support tool, we can use the left mouse button to paint surfaces where we want support to be applied, and the right mouse button to paint areas where we want support to be omitted. We then change our supports from everywhere to support enforcers only, and we can see that the whole model is ignored apart from where I painted that I wanted support. We can also right click on the model and come to add support blocker or add support enforcer. I'm going to add an enforcing box and then move it into position. Again, if I have support set to enforcers only, when I slice the model, only the sections that overlap will have support material applied. Let's consider if we have a 3D printer with multi-material capabilities. Dissolvable support material filament exists that is soft and flexible just like TPU. In these cases, we tell the slicer to print the support material with a different filament. We then pop the completed print into some warm water, something like 50 degrees, and after a few minutes it will start to soften and should be very easy to remove. You'll need to wash it to get rid of all of the little bits of gunk, but once you've done this, the result should be outstanding because you can have a very tight Z gap, and that will give you a very clean underside of the model as if the support was never there. You can achieve a similar effect with two filaments that don't bond to each other, such as PLA here in dark green and PETG in white. It's just a matter of setting support and interface to a second extruder, which will designate the two materials accordingly. This is the first time I've tried these materials together and it works surprisingly well. I only needed a little bit of massaging with my pry tool to remove the support between the two halves of the model, and then the support slid on out, giving me very clean undersides. In fact, the horizontal undersides were better than the angled overhangs on this model. If the secondary filament you're using is expensive, then you only need to print the interface material using it. That means only the support material that touches the model will be printed with the other filament, making the roll last much longer. There are exciting developments on the way to avoid support material altogether, as covered nicely by Stefan from CNC Kitchen. But until these methods are stable, hopefully this video is of use. Thank you to my patrons for requesting this video. Thank you so much to you for watching, and until next time, happy supported 3D printing.
G'day, it's Michael again.
Okay, so we got an idea about what support structure are, why are they necessary, and how we can try to avoid building those support structures. But wherever it's absolutely necessary, we need the support structures, as you saw in some of those diagrams. Some of these some of the building materials, you saw that the support structure was absolutely necessary. You could not avoid it. So yeah, that's the thing. And why we require the support structures, as the 3 points I have mentioned here. These are the points these are the answers to why the support structures are necessary. Then okay, so the thing is, we now know support structures are necessary. Then we now know why the support structure is necessary. But we need to answer the question when we can say that the support structures are necessary, or when we can tell that okay, now the material has to, need a support structure, without which the printing cannot be done. That is given from that we can obtain that from this formula. The formula of overhang structures. Here the overhang structure is given by D and the layer thickness is given by T. So the formula used to calculate the critical value of angle above which we need support structure is given by pi minus tan inverse of T upon D. This is the critical value. If the theta value, if the calculated theta value is greater than this critical value, then the support structures are necessary. And if the theta value is less than this critical value, the support structures are not necessary. So this answers the question of when the support structures are necessary to us. So there was one question which was solved by professor. I will solve that as an example for you. And then after we'll be solving one more question based on this formula. Just try to remember this formula, theta equals to pi minus tan inverse of T upon D. So this question was solved in the lecture as well. I will try to solve it again. Let's see. It is based on the formula which I mentioned above in the previous slide. In an AM process, the possible overhang is given as 1 mm. So D is given as 1 mm, right? And the build direction is Z direction. This is the build direction. The minimum possible layer thickness is given as this. The minimum possible layer thickness, which is given as T, is given by root 3 mm, right? Find out the critical value of the Z component of the facet normal to the triangles beyond which the support is required. That means we have to find the critical value of angle beyond which support structure will be necessary. Right. So that means let's find out this critical value. Let's find out this critical value, which will give you an idea, which will give you the angle which will be created while we use the T and D. This T and D, the specified T and D, which is given here, by using this, if we try to print this, what will be the angle? What will be this angle which is created is given by this formula. This is given by theta equals tan inverse. What was the formula? Pi minus tan inverse T upon D. Pi minus tan inverse T upon D. You have the value of T, you have the value of D, you have the value of pi. This will give you theta equals 120 degree. So to create this printing, the theta value is given as 120 degree. So how will you know that if this 120 degree is above the critical or below the critical? From this formula. If the angle and the build directions and the triangle normal is greater than theta, the support structure required will be alpha equals to this. And if this is a critical one, that means above which and below which we'll be calculating. So alpha equals to theta if it is critical. So therefore, this alpha 120 degree should be equated to this cos inverse. Because it has what is that? What has it asked? It has asked you the critical value of the Z component. What is the critical value of the Z component? Right? The building direction is the Z direction. What is the critical value of the Z component? As we are building in this direction, the X and Y components will be 0 because we are building direction is Z direction. So the critical value, that is alpha, equals cos inverse NIZ, because here NX, NY are 0, which is the only direction where the building takes place. That is the Z direction. Sorry. Sorry. Yeah, this is the D direction. Just the Z value is there. And this, for criticality, this will be equal to 120 degrees. So the cos inverse NZ is equal to 120 degree. So NZ equals minus 0.5. That means for what did I say? For this value less than theta, no support structure will not be necessary. So that means for alpha for nz value less than this 0.5, we have equated it to 0.5 because we are assuming that it is the critical one. But for nz value less than 0.5, support structure is necessary. But beyond that, support structure is not necessary. This is the critical value. Nz equals minus 0.5 is the critical value of the Z component. Uh, is the critical value of the Z component for which the support structure is necessary. Okay, let's try to solve one more question, which is based on this support structure. I'll give you 5 minutes to try this question. Then I will be helping you to solve this. Five minutes to solve this question. Here the bending direction is plus Z direction. Here the theta value is given. A, B, C points are given. A, B, C points are given. Critical value is 120, right? So if the angle, if the alpha is greater than 120, then support structures will be necessary. So we need to find out alpha. What is the value of alpha? One more trick for this solve this question, you need to find out the normal unit normal vector of the plane. There are three coordinates given. A triangle has been formed. You need to find out the unit normal. Okay, let me help you with this. It's a bit tricky question. Let me help you with this. Okay, so we have points A, B, and C. So A, B will be equal to what? To find out the unit normal, we need to find out AB and BC. What is AB? AB 1 minus the 1 minus 1 0 I cap plus 4 minus 1 3 j cap plus 0 minus 0, that's 0 k cap, right? This is AB. Then what is AC? AC will be 4 minus 1 3 I cap plus 4 minus 1 3 I j cap plus 4 minus 0 4 k cap. This is just vector addition, vector subtraction, nothing else. There are three vectors given. I am just finding the this vector adding the vector A, B, and B, C direction vectors, vector directions. I'm just finding that. Then how will you calculate the unit normal? Unit normal will be cross product AB cross AC. What will be the unit normal vector? So unit normal vector will be this cross this. What is the cross product of these two? You know the formula for cross product, right? This is cross this by. Okay, I will not tell you the formula for the cross product. You have to look for the formula for the cross product. So finding the cross product will be getting the value of normal vector will be 12 I cap plus 9 k cap. Is it plus 9? 3 into 3, 9, 4, 3, 0. Sorry, it will be minus 9. 9 I cap. 12 I cap minus 9 k cap. There is no j cap value. J cap is 0. You know to do cross product, right? You know how to do cross product, right? 0, 3, 3, 3, 0, 4, then again 0, 3. Then cross multiplication, cross multiplication, cross multiplication. This is how you calculate the cross product. AB cross AC. This will give you 12 I cap plus minus 9 K cap. Then this is the unit normal vector. Then the question says that the build direction is the Z direction, right? The build direction is the Z direction. That means we just need to ignore I cap because it is Z direction. So the unit vector of Z direction is K cap. So the I cap term is 0. So when we take the dot product of this N cap, K cap, the I cap term will be 0. So it will be, what is the value of cos theta? Sorry, let me just clean something. Eraser, clean this portion. Okay, so we have a building direction to be Z. That is, we have, sorry, let me write it clearly. We have N cap, that is the unit normal as 12 I cap minus 9 K cap. And our building direction to be Z, right? Equals K cap. So when we take the dot product of this two, n cap dot k cap, what will we get? N magnitude, k magnitude, cos theta, right? Or cos alpha. This alpha we need to find. How can we find that? This was the question. We need to find alpha if it is greater than the value of 120. We need to check that. So alpha equals n dot k upon n vector magnitude, k vector magnitude. What is n dot k? K is just k and n is 12 minus I. The x unit vector along x direction will be 0. So it should be minus 9 upon 12 square upon 9, 12 square plus 9 square plus 12 square plus 9 square plus, sorry, multiplied by 1 square. This will be the magnitude. So minus 9 upon 15. When you do this, you will be getting 15. Root over is there. It will be root over of 2 to 5, then 15. So cos alpha equals minus 9 upon 15. So alpha will be equal to cos inverse minus 9 upon 15, which will be equal to 126 degrees, approximately 126 degrees. So what the question says that it should be the critical value is 120 degree, but we are getting an alpha value to be 126 degree, which is 6 degree higher. That means support structure is necessary. Does this triangle require a support structure? Answer will be yes, because the alpha value is 126 degrees. So this is how you solve the questions. Okay, let's leave it till this. We'll be starting on slicing for the next section, because we solved a lot of questions and in detail. So, okay, let's stop it right here. Thank you so much for attending. We'll meet next Monday. Anyone have any questions? Anyone having any questions? Otherwise, we can leave.
Tomorrow we have also a lecture.
Yeah, tomorrow we have a session. I told you, so there are 3 tutors for the session. One is on Friday, one is on Monday, that's today, and tomorrow on Tuesday, we have one more session. But all these 3 sessions, the course contents will be same, because 1 week course content will be taught in this section, in this week. So on Friday, on today, and on Tuesday, what will be taught, everything, the course content will be the same, but the tutors will be different and the approach of teaching will be different. So you can attend the other one as well and see if you like the other tutor. It's up to you.
Okay.
Whichever
Okay,
you
sir.
attend. There is no restriction to you.
Yes.
Sir, I have a question, sir. I don't know how to submit the assignments.
Okay. You just have to click on the options. Then you have to submit at the end of your questions. There'll be a submit option. You just have to click that. Nothing else.
Sir, on
Let
my
me show you.
email,
Let me just.
sir, on my email where I get the information about the class.
You are you registered in Swam portal?
Yes, sir, I have registered.
Yes, in the Swam portal, you can access to the you should have access to your assignments in the Swam portal.
Right, sir. Right, sir. Thank you very much.
Let me show you once again.
Please,
Let
sir.
me show you. Yeah. Okay. So you just share my screen. Just give me 1 second. Okay. So you have seen this coming up in your when you open the SWM portal. You have seen this coming up, right? Do you see this coming up in the SWM portal? The person who asked the
Sir.
question, I'm asking.
Right, sir. Right, sir.
Okay, yeah. So when you click on week 1, then you go to week 1 assignments. You click on week 1 assignments. You see these assignment questions are here. Then you have to select all the options. Then you have to click on submit answers. Then it is submitted.
Got it, sir.
Okay, perfect. Any more questions? If there are no questions, we can disperse. Thank you so much for attending. Have a
Thank you,
great
thank you,
night.
sir.